Great. Well, it's nice to give this lecture here, as Weizmann for many years has been a center for both experiment and theory in 1D. It turns out that one-dimensional fluids are different in some interesting ways from what you just heard about, and it's also worth learning about that. Even if you don't care so much about one dimension for its own sake, it's a good way to clarify what are some of the assumptions made in the standard theory of fluids and where might those need to be modified for some physical systems. And it turns out the main punchline, and it'll take me a while to try to convince you of this, and in particular there is some mix of a few derivations but also a lot of pictures and numerical confirmation and analytical confirmation by other methods and so on. But basically there's been a lot of progress in the last couple of years in what kind of fluid dynamics describes some one-dimensional systems, and how instead of just 3 Euler equations, you have some infinite list of Euler equations, and yet it still winds up being solvable. And that really could have been done in the 1980s. It was done more or less for classical systems around 2005, and then rediscovered for quantum systems, or it works surprisingly well for quantum systems, maybe since 2016. So even though fluid mechanics is very old, some aspects of one-dimensional fluids are fairly recent. I have some mix of a little bit of pedagogy and then a little bit of research. Please interrupt me, and I will present a few things maybe on the board, but mostly I'll just use the board if you ask me questions, because I have things like numerics and so on that would be hard to present on the board. And one sort of trend you'll see, so you've already heard about some of the history of fluid mechanics in the continuum, starting with Bernoulli and Euler and people like that. A sort of complementary picture that goes back at least to Boltzmann is to think about particles. So maybe your fluid is made up of particles. The dilute gas of classical particles is one of our best examples of a fluid. And those pictures are generally somewhat different. They're about different quantities. The Euler picture is about your conservation laws, your conserved quantities, and the Boltzmann picture is about the one particle distribution function. Those turn out to be especially closely connected in 1D. They're not as different as they usually are, and I'll try to explain why. And then my second lecture is going to be higher dimensional. So the 2 questions I want to talk about, and I want to start by reminding you a little bit about transport in solids. So this lecture is going to be a bit more connected to electrons in solids. So there's an assumption we make for various reasons, both for fluid mechanics and for linear response theory, that whatever initial state you give me will eventually relax to some kind of thermal state, to be precise, a Gibbs ensemble state that is determined by whatever the conservation laws are of my system. So there are some other possibilities. One is that the system might just not thermalize, at least not in any conventional way, and many body localization has been sort of an active example of that in recent years. Some other ways that a system might fail to have conventional thermalization to the standard Gibbs ensemble would be, what if there are extra conservation laws beyond particle number, momentum, and energy, which were kind of the 3 key conservation laws in the last talk. And that may seem somewhat artificial. It turns out that in one dimension it's quite natural. In fact, the main one-dimensional standard Hamiltonians that we care about, both for atomic physics and for solid-state physics, tend to have this special property of having infinitely many conservation laws, and I'll try to remind you or explain to you why that's true. And then the immediate question you might ask, well, there's one question that experts would ask, and there's another question that I would have asked a few years ago, and that was, if you've got a real system, we think that in the laboratory, say, you never have perfect conservation of this infinite list of conservation laws once you add perturbations that are probably there. Maybe your system is not exactly one-dimensional, maybe there are extra interactions between the particles, whatever. So how much of this integrability and special hydrodynamics survives? And we can answer that in a few cases. And another question that people might ask, which I probably won't say much about today, but I could in the next lecture if people care, it turns out that the low energy limit of one-dimensional electron fluids is very special. It's not the ordinary Fermi liquid metal we get in higher dimensions. It's something called a Luttinger liquid. A lot of the basic experiments on that were actually done here. And in a sense, it's almost free. It's even simpler than what I'm going to talk about. So if you've ever heard of the Luttinger liquid, and if you're used to thinking of one-dimensional electron systems as free, that's only true at very low energies. And what I'm going to talk about is a somewhat more general picture. But there are some connections between them that I wasn't planning to talk about, but I could. OK, and then other things in higher dimensions later on. So Einstein was a very clever person, and one of his many contributions to physics was to teach us how to compute things like conductivity. So when we're thinking about a solid, we don't normally, until recently, until very clean materials, we don't really think about the electrons in a solid as necessarily being a fluid. How do we approach them, and how is it a little bit connected to fluids? Well, Einstein made the point that there's a nice recipe to compute things like diffusion constants, for example, which is an example of a linear response. If I've got some density of large fluids, Brownian particles, floating around in a fluid, well, you've probably heard that when people first looked at a heavy particle in a fluid, they saw the heavy particle jiggling around, and they assumed, aha, well, therefore the heavy particle must be alive. That was not quite true. It was just executing random motion because of the system being at finite temperature and it being bounced around by the little particles. So if I have some gradient in density of these heavy particles, that will eventually return to constant density, and the rate at which it returns, the diffusion constant, so this is a restoration to equilibrium from a non-equilibrium initial condition. That's actually given by dynamical correlation functions at equilibrium. And this is true in classical systems. That's what Einstein was thinking about. But it's also true in quantum systems as well. And it's a very useful principle. So the precise form for this diffusion constant is that if I watch a Brownian particle at thermal equilibrium, then, well, its velocity fluctuates. It does some kind of random walk. Its velocity only has a memory for a certain amount of time. Let's call it tau. Basically, the diffusion constant is of order velocity squared tau because of this relaxation or forgetting. And that's kind of remarkable, that the same thermal equilibrium fluctuations control the restoration of equilibrium. And the basic philosophy of linear response that this reflects is how a system gets back to equilibrium doesn't really care whether you pushed it away by applying some force or whether it fluctuated away, because that's how temperature works. Things fluctuate. So in metals, in quantum systems, we use exactly the same idea. It just looks a little bit more complicated. But the key idea is still some dynamical correlation function equilibrium tells us about linear responses. So there's, in fluids, going to be a weaker assumption. But for standard linear response, we assume that globally the system was weakly perturbed from equilibrium, and we can compute things. And this is how we compute, say, electrical conductivity. So when we normally think about transport of charge in a solid, and we're not thinking hydrodynamically, we're just thinking about how does a current relax. And there's a whole art to computing these kind of correlation functions. But if you, say, take a first course in solids, you don't compute the Kubo formulae much. You use this Boltzmann approach a lot more. It's much simpler. And here I've just written it up. And you've probably seen this before, but I'll quickly sketch what it is, because one of the heroes of the story I want to tell you is a modified version of the Boltzmann equation for 1D fluids. So the idea of the Boltzmann equation, let's just think again about a classical dilute gas, even though we use this for quantum systems as well. I've got a one-particle distribution function, which means this f, that's a function of position, time, and momentum, say. If I just looked at the left-hand side, and I could add an external force, which would be like f dot d momentum f1, the left-hand side would just be independent particles streaming along. This is the statement that the distribution function doesn't change along a trajectory if I just have one particle physics. It would be like df dt is equal to 0, where it's the total derivative, the sort of Lagrange derivative. The right-hand side, you've probably heard, is where all the magic happens. So Boltzmann wrote this down basically phenomenologically. He said, well, okay, if I've got one particle moving independently, not that much exciting stuff is going to happen. Let's have particles collide. The form of this, so W is something about the details of the collisions in the system, just two particle cross sections and so on. This part is saying, well, there's a positive term, which is that particles at different momenta scattered in, and there's a negative term, which is particles at momentum 1, the one where I'm evaluating the left side, got scattered out. And this gives increase of entropy and so on. And a nice fact is that with a bit of work, you can derive the equations of fluid mechanics from something like the Boltzmann equation. But the Boltzmann equation, the dilute gas of particles, is just one example of a fluid. There are certainly fluids that satisfy the fluid equations that do not have this kind of particle interpretation. The fluid equations are more general. The flip side is that this has more information because this is talking about the full momentum distribution, while the standard Euler equations are just a few properties. They're just things like density, momentum, and so on. Effectively, they're integrals over this distribution function. Anyway, so all of this is going to be modified when I come back to it, but this is the traditional Boltzmann equation. So there's a particular problem that people were studying, including us, in 1D for a long time, and that I want to sort of trace through because it's what led to thinking about fluids in this new way. It's maybe the simplest far from equilibrium problem you could ask about one-dimensional transport, the so-called true reservoir quench. And basically, step by step, you can learn a few things about that, starting with, say, a free model. And then you take an interacting model, and well, maybe you can't solve it completely, but you can say some things about it exactly. And then more recently, people figured out how to say some things very general and exact. And best of all, you can sort of check them, at least for some models. So I'm going to define a couple of standard models. You've probably heard of the Hubbard model. I'll mostly talk about an even simpler one, which is the so-called XXZ spin chain, or one-dimensional fermions with nearest neighbor interaction. And I'll write up the Hamiltonian in a second. This is just kind of an outline. But basically, by starting with the simplest possible problem, you get led to some things that are more general. So that's also the way the history worked. So I thought I would do it that way. And then you can test the picture that you get out of that in more general circumstances. And the basic equation I'm leading up to is sometimes called a beta-Boltzmann equation. Basically, it's a Boltzmann equation for the particles that we use to solve interacting one-dimensional problems like the Hubbard model and so on. And even if you don't have a huge interest in beta ansatz or integrability for its own sake, just think of this as a funny kind of fluid where some of our standard assumptions about fluids still work and some of them don't. So at least it's a way to teach you something about fluids. And then, yes, we can check a lot of what I have to tell you, and I'll try to convince you of that rather than by very long derivations. So zeroth order hydrodynamics, if you want, you could derive it from the Boltzmann equation as a complementary derivation from the last lecture. If we were in 3D, I would have two scalar equations and one vector equation. This is continuity. This is coming from the fact that the number of particles is conserved. So n is my density and u is my average velocity. And these appeared in essentially the same form just in the last lecture. So zeroth order means I'm not including viscosity and things like that. So I wouldn't necessarily reach global equilibrium with these equations. The problem with these is they have false equilibria that most real fluids don't have, but suspend your disbelief for a moment. This is the velocity equation or Navier-Stokes equation, whatever you like. It doesn't have viscosity, so it's not the full Navier-Stokes equation. It comes from conservation of momentum. And this is the heat flux equation from conservation of energy. So the key assumption that went in going from just continuity equations to this particular form, which is a closed set that we could try to solve, is local equilibrium. So if you think about a fluid like air or water or something like that, if you were given some initial microscopic state, ignoring the fact that you could never measure the microscopic state of 10 to the 23rd particles, you wouldn't really know what to do for at least a couple of collision times, for say a few nanoseconds. But once a few collisions happen, our assumption is that it starts to be meaningful in a fluid like the air in this room to talk about there's a meaningful temperature and velocity here, there's a meaningful temperature and velocity here, and so on. We assume that there's some local equilibrium, and then hydrodynamics is really the process, at least what we use the equations for, is to get from local equilibrium to global equilibrium if we wait long enough and if we add the right terms like dissipation and so on. So in the systems I'm going to talk about, even the notion of local equilibrium is different. There is still a notion of local equilibrium. It's so-called generalized Gibbs ensemble. And I want to say a bit about what makes these systems special and why this is kind of unique to 1D. But even this first step of local equilibrium is going to be different. But we have known for a long time what is the right kind of local equilibrium in one dimension. So then the only new thing is to try to figure out how do those local generalized equilibria evolve in time. So I'm going to talk about two examples when I need to do something concrete. One is just take bosons, non-relativistic quantum mechanical bosons moving in one dimension, and let them have some repulsion that is just a delta function between them. So that's the so-called Lieb-Liniger gas, and it's realized in atomic physics laboratories. And that's the simplest model to solve with the kind of methods I'm going to talk about. It was the first method whose exact 1D thermodynamics were solved by Yang and Yang. They sort of invented what's called the thermodynamic Bethe ansatz. A model that's easier to check because it's on a lattice, and that makes it easier to do some kinds of numerical checks, is the so-called XXZ spin chain. So the original model that Bethe solved the ground state of when he was a graduate student, it was 1931, was the Heisenberg chain. That is the nearest neighbor spin-half antiferromagnet in 1D. And it's a great paper. He just basically thought about a few particle scattering, more and more particles, built up the ground state, and then said, well, higher dimensions will follow soon in the next paper. So we're still waiting for the next paper, but it was still an incredible accomplishment. In 1D, there's something very special going on, and it's kept mathematicians busy since about 1931, understanding what he did, really. So anyway, this is not quite the Heisenberg model because I've let the XX interaction be a little bit different from the ZZ interaction. So I've assumed the XX interaction and the YY interaction are the same, let the Z interaction be different, and later on I might want to add either a constant or a spatially varying magnetic field. So this has another way of looking at it. You can transform it through the Jordan-Wigner transformation to a one-dimensional fermion system with nearest neighbor interactions. And I think I have that form of the Hamiltonian later on, but it's really exactly the same Hamiltonian. It's another nice thing about 1D, that fermions and bosons are not so different. Okay, so what makes those models like Lieb-Liniger and the XXZ chain or the Hubbard model special? And here, I'm going to quickly go through what Bethe did, basically. And this is your lightning course on the Bethe ansatz, but the idea is very simple. Making it work in practice is sometimes a little complicated depending on the model, but not really for Lieb-Liniger. So what happens is when you start taking a few particles, so let's do Lieb-Liniger. This is the Hamiltonian. This is just a bunch of one-dimensional bosons, let's say some finite number n, moving in the continuum with a delta function repulsion. So C is positive, and I've made this coefficient 1 to keep life easy. So if you had one boson, you know how to solve that. If you had two bosons, I think you probably still know how to solve it in 5 minutes or so. So 3 bosons, 4 bosons, 5 bosons. In general, that would be very hard, but for this model, 3, 4, 5, and so on, you notice a pattern that makes it pretty, not particularly difficult to solve even for some large number of bosons. And then eventually you can take the continuum limit and even go to finite temperature and do this thermodynamic Bethe ansatz. So the history is basically that what I'm going to tell you now is fairly old, and people knew even how to get exact finite temperature results for thermodynamics for this class of models starting in the 70s. But dynamics were very hard. The only dynamics that people could do were sort of few particle, maybe 2 particle correlation functions. Even that was a lot of work. So the recent progress by a lot of people, and as I said, this really goes back to classical models around 2005, to be honest, and I have that citation later on, is realizing that the same techniques also give you hydrodynamics. Not every dynamical problem, but the dynamics of densities that we normally study with hydrodynamics, these are good methods for. Okay, anyway, let's do the Bethe ansatz. So, well, we know that the solution of one particle is a plane wave. So let's take 2 particles, and what I have to do is match my plane waves on the points where x1 is equal to x2 for 2 particles. So I'm going to write my wave function in this form, the beta form, which is I've got my particle locations, x1 to xn. I've got plane waves with some momenta k. And then the only remaining degree of freedom, well, I might permute my particle labels, and I have to figure out the coefficients for each particle label. And let's see how that, let me connect this to what you would have naively done maybe for two particles. So let's do it for c equal to infinity and see how actually c equal to infinity in this model basically transforms the bosons into fermions, for thermodynamics at least. So if c is equal to infinity, then I need the wave function to vanish, because then the coefficient of my delta function is infinite when the two particles are on top of each other. So if we do two particles, I would be tempted to write plane waves when the particles are not on top of each other. And then I just need to figure out these a coefficients. But by that requirement that the wave function vanish, I've only got one thing I can do. These have to be equal and opposite, which means that my wave function is now determined up to some overall constant that doesn't really matter. And I can write it in maybe a more suggestive way. I can write it as a Slater determinant of two plane waves at momentum k1 and k2. So this part, you could basically do this for any interaction, even if it was more complicated. The two-body problem is not too hard. The special part is going to be that this beta form works for any number of particles for this interaction, which in general isn't true. So what you do is go to n equal to 3, and maybe now let's let C be general. I start matching at all the collision points these a coefficients. And in general, I run into a problem. I start to have more requirements on my coefficients than I have free parameters, which in general means there's no solution. And for a general interaction, if I gave you something that was not a delta function or 1 over r squared, but some other power or other functional form, I would run into trouble. But for some special interactions, there's a certain magic that happens. And basically, the point of this lecture from now on is going to be to figure out the physical consequences of this magic for dynamics. The basic idea is that when I bring particles together in some of these models, however many collisions happen, the end result is independent of what order the collisions happened in. That's sort of a physical meaning of the fact that there are not as many, I don't wind up having to satisfy as many independent relations as I thought I would. These ratios all wind up collapsing in a very simple way. And the way we normally draw this is something called the Yang-Baxter relation, which is three particles coming together, and it doesn't matter whether A and B collide first or A and C collide first. In general, what's special about integrable models, and we're going to translate this to hydrodynamics, is that you've got any number of particles coming together, and after they've come together, they all come out with the same momentum they went in with. There's just a phase shift. So normally, if two particles came in and then came out in 1D, well, two particles, that's true in general, that their momenta will be the same by energy conservation, and there will just be a phase shift. The magic here is that somehow even many, many collisions happening at the same time don't seem to give me dissipation and normal thermalization and things like that. So that's one way to look at why integral models are special. But there's one consequence of this that you can actually work out from this Yang-Baxter relation. Let me skip over that, which is that there are an infinite number of conservation laws. In Lieb-Liniger, these are fairly simple. And here, this is an example of why I'm trying not to do too many explicit derivations for xxz. Let me tell you what these formulas mean very briefly and why it's kind of an interesting example of what we're going to need to include in the fluid mechanics. So xxz, this was some simple spin chain. It was just nearest neighbor interactions in a 1D lattice model. And the point is, okay, you'd say, well, energy is conserved, and I didn't see. No, that's fine. Yeah.
This sequence infinity case is kind of confusing. So I understand the wave function must vanish at the point where the particles cannot be together, but they are bosons. So don't we need to impose that the wave function will be symmetric afterwards?
The overall wave function will be symmetric under exchange.
So what did we look at? Why does it?
Well, this is why I said for thermodynamics, basically when you the way it works is the bosons, the effect of the interaction is that there is something like an exclusion principle. So one momentum, so when I think about putting the bosons in a box and ask what are the physical consequences of this, basically there will be, if I occupy one bosonic momentum, then the other boson will see a phase shift when it goes through the first one, and that will mean that its effective momentum is different. So effectively, I get an exclusion principle out of the interaction, even though it's still a bosonic symmetric wave function.
But still I would have a symmetric wave function.
Yes.
Well,
note that here, okay, remember I'm only writing my wave functions for a particular ordering. And then I define it for other orderings by symmetry.
So if you change the ordering,
it will be symmetric. It is a symmetric. It is compatible with both statistics. Yeah, I mean, just yeah. So a more surprising, maybe, consequence of that is when I ask what are the conserved quantities of this simple either Lieb-Liniger model of bosons or XXE model of fermions or XXE model of spins, it turns out that spin along Z, energy are just the first two of some infinite list of conserved quantities. They get more and more complicated, but they all have some nice features. And this is just to prove to you that they exist. And there's one special thing about this model that turns out to give you some far from equilibrium results that were then an important check on the hydrodynamics. But basically, I've got some infinite list of conserved charges and some infinite list of conserved currents. So the first two conserved charges, Q1 would be spin, Q2 would be energy. Q3, this notation means sigma x on one site, sigma y on the next site, sigma z on the next site. So it's a three-site operator and some complicated combination. And this quantity, if I sum it over all the sites, is a perfectly good conservation law. It commutes with the Hamiltonian, and it commutes with the first two. So then I go, and there's one more, and there's kind of a rule to generate these. It turns out there was an infinite list of these, but people were still missing half of them until 2011. And as a result, there were some questions about the physics they didn't get quite right. I'll try to say a bit about that later on. But basically, integrable models, the reason why we call them integrable, if you remember your classical mechanics, we would call a system of harmonic oscillators integrable because there is effectively one conservation law for each degree of freedom. So as a result, we know the dynamics of harmonic oscillators is pretty simple. So this is a quantum version of that. We have some infinite list of conservation laws, and at least once you include the new ones from 2011, there are enough that we might expect that the dynamics of the system is not very chaotic. Maybe it's like a set of harmonic oscillators in some very vague sense, and making that less vague is the point of this hydrodynamical approach. Anyway, so this is my infinite list of conserved quantities. And with these, there are currents, the same way that, for example, if I look at spin, there's a spin current, or fermion number density has a number current. Here, this is kind of an interesting fact that is a bit special to XXE, and there's one quantity that appears in both infinite lists. So there's an infinite list of charges and an infinite list of currents. The energy current is itself a conserved quantity. And that's the first sign that maybe my hydrodynamical equations are going to need to be a little bit different. That if energy current is itself conserved, like energy, then maybe I should write a hydrodynamical equation for it. So that one little fact will come up later. But in general, they're just two infinite, increasingly complicated lists. And they're all sums, translation invariant sums of local quantities. So that's integrability. Now we can go back to doing some physics. One quick note is you might, if you've heard about the XX model, which is set the Z interaction to 0, that's actually free fermions. Free fermions in 1D, you could say, well, I know how to solve that. I write the occupancy and momentum space as my conserved quantity. In other words, the Hamiltonian would be like essentially, well, let's include an energy. So there, it's true that these are now conserved quantities, but these are actually very different, and this representation only exists for the non-interacting case, basically. So here, this would be what I might call n sub k the number of electrons at a particular value of momentum. These are not local. These n sub k's, they are conservation laws, but they're not local in the sense of those, and in general they are not very useful for trying to understand thermalization and things like that, so that's why I don't have much to say about them. Okay, so, and this is just saying what I tried to say in words a moment ago, that we know in classical physics, if we have enough independent conserved quantities, things change a great deal. We lose chaos and we get some kind of order. What about in quantum systems? And I want to get to what exactly happens when you have all these conservation laws in a quantum system, and then we can try perturbing away from it. So here's the two reservoir problem to try to build up some intuition, starting with free models and then asking what might interactions do. So I'm going to take a simple 1D lattice model like this. I want to take an infinite one-dimensional system. I want to heat the left-hand side to one temperature. I want to cool or put the right-hand side at a different temperature and then let it go. So this was the system at time 0, and I watch it evolve in time. And in particular, these temperatures don't have to be very close, so this could be quite far from equilibrium. And the challenge is, well, if I wait long enough, do I get some kind of steady state at the junction? What are the properties of that steady state, and so on? So this is maybe your model, far from equilibrium hydrodynamic problem, now for a quantum fluid on a lattice. So let's warm up with maybe easy cases, yeah?
In this setting, is the initial condition important?
Basically, later on, for hydrodynamics, we think we can solve a much more general set of initial conditions. But there are a few things that we can only do for this very special one. So this has some advantages, is probably the way to put it. So it's pretty important, but for now. Even at the end, let me maybe skip ahead a bit. So like normal hydrodynamics, the assumption of the initial condition is local equilibrium. That is, hydrodynamics doesn't really tell you how you got the local conserved quantities, but there they are. The same thing is going to be true here. So the initial condition will be local generalized Gibbs ensemble. And we think that that onsets, again, in a few collision times, unless you go essentially to 0 temperature. That's kind of a pathological limit. We think it's a little bit like in normal hydrodynamics. If you took a normal fluid, I think it would also, you would need a very large fluid cell, and you would have to wait a long time if you were taking the limit of 0 temperature. So yeah, eventually we'll have more general initial conditions, but for now, let's take the simplest one I can think of. Okay, equilibrium would be the simplest, but that wouldn't evolve. So this is the second simplest. So here's a picture for what goes on, and it turns out that in interacting models, there's something surprisingly similar to this that still works if you ask the right question. And that was sort of a clue that there must be more structure. Anyway, if I've got a free model, or conformal field theory for experts, this is also true, then let's say the left lead is hot and the right lead is cold, and I let them go. Particles fly from both sides with the corresponding temperature. And the main point is, in a free system, it's already not going to satisfy ordinary hydrodynamics because there's no local temperature if I'm at this point. My right movers have a different temperature than my left movers. So that means it doesn't make much sense to talk about the distribution of particles here as one temperature. You would need at a minimum 2 temperatures. And what happens as far as the current is very simple. The reason why I called it the Stefan-Boltzmann picture is just the Stefan-Boltzmann law for a black body, to remind you, is the total radiated energy from the black body. Here, if I sit at this point and I'm in 1D, I basically get an energy current, which is like the total radiated power from the left side minus the total radiated power from the right side. So if you like, you can compute that, for example, for free bosons. A neat little fact is that you get the so-called quantum of thermal conductance, which is the same for fermions or bosons or anyons. I won't work through this, but if you want a neat little exercise, try solving that problem with the 2 reservoirs for either free bosons or free fermions, and convince yourself that you get the same answer. You get this, this is kind of like E squared over H is a little bit more famous. That's the electrical conductance quantum. So this is some number times K squared T over H. That's the thermal conductance quantum. Okay, so I want to now turn on some interactions. And the first thing you might worry about is maybe once I turn on interactions, I start to get local temperature, so that picture of left movers and right movers no longer is useful. It turns out that neither independent left movers and right movers nor local temperature is going to work. But first, since this is a school, a little bit of background on when do we expect dissipationless transport. When might we expect also that there's no local equilibrium? And the way that's normally codified is as a breakdown of the Kubo formula, where you get a divergence at zero frequency in some kind of conductivity, either electrical conductivity or charge conductivity. And the weight of the delta function is called the Drude weight. So we know a couple examples in condensed matter where this happens. In higher dimensions, you get a sort of transport by the condensate in a superconductor, most famously. And then there's a different mechanism, which appears a lot in 1D and sometimes in higher dimensions, which is the following. So this is writing out from the Kubo formula what this coefficient will be. So normal conductivity, I'll get a finite answer at zero frequency if this relaxes. If as t goes to infinity, this goes to zero in such a way that there's a finite integral of j of t, j of zero correlations, and I'm not writing out commutators and so on to be precise. This is the idea. If you now don't have this go to zero, that corresponds to a delta function, and the easiest way that can happen is the following. Suppose, for example, I had a one-component fluid and momentum was conserved, and I asked about what's the charge conductivity. Well, in that case, the charge conductivity is usually proportional to the momentum. So if I look at this integral, whatever the momentum was at zero, it's the same value at t, so this doesn't fall off at all. So in other words, the fact that momentum is conserved in a one-component translation invariant fluid tends to give you an infinite conductivity. And this is sort of the mathematical formulation of that if I've got conservation laws Q sub k that are part of the current in the sense of having a non-zero overlap with the current, then any perfect conservation law gives me a piece of the current that doesn't fall off. And this is called the Maser bound. This is one way to get dissipationless transport. And as a sort of recent non-trivial example of this, let me explain this discovery about XXZ in 2011, which was made by Tomáš Prozin in Slovenia. So the thing we knew for a long time, going back to say 1970 or so, was that this model, this spin chain, had an infinite list of conserved quantities, and we could solve its thermodynamics exactly. But as an example of how transport is harder than thermodynamics, we didn't know if it actually had ballistic transport of spin or charge. It did have ballistic transport of heat. That's relatively easy. Basically, the challenge was we knew all these conserved quantities. I showed you that infinite list before. None of those give you any contribution here. That is to say, all the conserved quantities turn out, for very simple symmetry reasons, not to overlap with the spin current. So that was not helpful as far as trying to establish ballistic spin transport. And then Prozin found a totally new kind of conserved quantity. So it turns out that even though we thought this model was old news, there was something very big about it that was missing until this nice PRL. It's really quite a breakthrough in the integral models community. One message of today is that you don't actually need to know all this to get correct dynamics of the model. In a sense, rather than working with the very complicated conserved quantities, there's a much easier way that gives you the right answers for things. But to be fair, this really was an important step in kind of getting people to think about this model some more. So let me now say, how can you get one exact result in the interacting case that's going to be a check, a way that we know that the hydrodynamical approach is working, aside from just numerics and so on. So there may be two questions that you would ask if you're an experimentalist about what you could measure in this 1D system. And the standard question that you ask is a bit different depending on whether you work with atoms or electrons. So condensed matter people mostly think about what is the current I could measure of either particles or energy through the junction. And that turns out to be hard. That is solved by the new hydrodynamical methods that I might just get started on by the end of today. Another problem is a kind of expansion where with atoms, what you might do is take a picture of how the atoms or how the energy moved around. You would get the spatial profile and try to characterize that with one number. And it turns out that there's one question about expansion that is exactly solvable with the very simple form of generalized hydrodynamics. And then the full form of generalized hydrodynamics, which you need a computer to solve, is going to give you that and other things. So Anyway, this has some experimental relevance. I think in the interest of time, I'll skip over why people care about Lieb-Liniger. This is what I mean by an expansion. So I've got my two reservoirs. I start evolving at t equal to 0, and after a while this gets smeared out, and I could look at something like the change in the first moment of particle density or energy density as a way to ask how much has the system changed from where it started. And another type of experiment, which is a little bit different, is to let one reservoir expand into vacuum, but that's also interesting. And then I'm going to quickly sketch, try to maybe, like in the previous talk, ask you some questions in a moment about why this is solvable even far from equilibrium if I ask the right quantity. So the magic is going to be that there are some problems, and energy current in XXZ is the one where this is most confirmable numerically, where you have a current that is itself a conserved quantity. What I mean is that energy current is the current of energy, but if I integrate it over space, it gives me itself a conserved charge. And this means that for the right questions, far from equilibrium reduces to an integral over linear response, and linear response we know how to do. So let me sketch that. Yeah.
Small j is the energy current?
It could be, it's any current in the model that has this property, but for XXZ, for where I can check it on a computer, it's energy current. In Lieb-Liniger, it would just be particle current. But Lieb-Liniger I can't check as well. But I mean, I'm sure it's true at this point. So anyway, what I mean by first moment is something like this. This would be first moment of either of a density, let's say energy density or particle density. That's related by continuity to a current, which means the change in time of the first moment is this spatial integral. And what does it mean? Let me try to draw a picture for why this fact means that far from equilibrium, nonlinear response might be pretty simple. Let me skip over that. So what's going to turn out is that for the right quantities like in XXZ, so I'll sketch my picture in a second, it's going to be a little bit like the Stefan-Boltzmann case in that some facts about the long-time energy current between two temperatures are not arbitrary functions of the left-hand temperature and the right-hand temperature. They're one function, something like a generalized Stefan-Boltzmann law evaluated at these two. So this is already greatly constraining the physics. It means that you can write it in sort of a cyclic form. Something about the energy current from T1 to T3 is given by the sum from T1 to T2 and then T2 to T3, and this is something that Ronnie Alon, Christoph Karish, and I were obsessing about a few years ago. Let me give our picture for why this is true. Okay, I'll come back to that in a second. Here's the picture, and then I'll give you the equation. The picture for why this is special. Suppose I've got now, instead of the 2 reservoir quench, the 3 reservoir quench. So my initial condition is 3 temperatures. And the only fact I know about the system is that the total energy current, let's say, is conserved. And so that means if it starts at 0, it's still 0. What that means is, now suppose the reservoirs are big so that these junctions don't talk to each other. I let the system evolve. Then there's some current from T1 to T2, some current T1 to T3, some current T2 to T3. To be precise, the spatial integral of the current in the junction region is what satisfies this form. But the point is that sum being 0 means that if I know what's going on between, say, T1 and T2 and between T2 and T3, then that determines what's going on over here because the sum has to be 0. So there's a kind of, the left hand knows what the right hand is doing because of this global conservation law. If you want a more serious derivation of that, what you do is you work out hydrodynamics with one extra equation, where this is normal energy continuity. This is the fact that energy current is itself a derivative of something else. So you combine those two, and you get some far from equilibrium results. And it turns out that these are in a way now, so this is what I was saying about the total energy current is 0 means that there's some kind of sum relation or cyclic relation between these 3 junction regions. So this gives you some exact results that you can check numerically. I'm not going to get into them much because they're almost obsolete now, given the new hydrodynamics. But let me show you. So the claim is I can do some exact results for expansions of energy in XXZ and things like that. This means that there's sort of a non-equilibrium version of Maxwell relations and so on. If this was 2015, I would tell you more. but I'm going to mostly focus on these as checks on this more general hydrodynamical picture. But first, when I say check, here's what I mean. So these are comparisons to density matrix normalization group, which is a very sophisticated numerical technique in 1D that we think is pretty close to exact for this question. Those are the boxes. So the quantity is the total current and how that's increasing in time across the junction between one lead at infinity and the other at some other temperature, the horizontal axis. This is the free problem. Everyone can solve the free problem. This is the Heisenberg chain, so this is pretty strongly interacting, and yet, with no free parameters or anything, you get this exact answer. So at least for the right quantity, something about far from equilibrium is given by an integral over linear response. What do I mean by integral over linear response? Well, if I go back to this picture, suppose I wanted to know the answer for some big difference between T1 and T3. Well, I could put T2 halfway between, and then I've got to solve the problem of two smaller temperature differences. If T1, then I could solve each of those by doing the same thing. So I could take a big temperature gradient and keep chopping it up into smaller and smaller temperature gradients until it becomes an equilibrium problem or a near equilibrium problem, and those I kind of know how to solve. So that's what I mean by saying for the right question, far from equilibrium becomes an integral over linear response. So now, in my last 10 minutes,
Does this, I think, exclude the energy current that are circular?
Well, I started off with my assumption that the total energy current was 0 in the initial state, so it will remain 0. So there could be a non-zero total energy current, but I didn't put it in my initial condition. Yeah.
So it's excluded.
For that problem, yes. But now comes the relaxation of those. So the first works in 2016 figured out how to solve the two-reservoir quench for even things other than energy current, basically the full profile of how things evolve, and then I'll tell you how we can generalize that to arbitrary initial conditions, basically. So now, even if you didn't care too much about the two-reservoir quench, let me sketch why this works. And the idea is actually that the hydrodynamics of quantum integral models is surprisingly similar to the hydrodynamics of classical integral models in a form that was worked out by these people. And I'll show you, I think as my last slide of the day, that it works pretty well, by my standards at least. Even if we can't go to the perfect long-time large system limit, it's surprisingly useful. So here's the basic idea. And this form was written down first, I think, for this paper is maybe not as well known as it should be, although now it's being rediscovered. First, you have many solitons in the nonlinear Schrödinger equation, which are basically classical particles that behave like Bethe-Ansatz particles in a sense. So the idea is that Boltzmann equation I wrote down before gets modified to the following form. It looks simple. In a way it is, but it's more complicated in some other ways. So I don't have any collisions. Hooray. And that makes sense because we know that a integral model doesn't really have dissipation or relaxation. The same momenta coming in come out, so there shouldn't be any collisions. But how do interactions do anything? Well, the magic is this term where this is saying the velocity, so I'm looking at the time derivative of momentum k at space-time point xt. And the point of this term is that the velocity that I should use for that momentum depends on the density of all the other momenta at the same space-time point. And what's going on, the picture of that is very simple. It's that in an integral model, particles interact with each other. They make a phase shift, but what that means at long distances or kind of semi-classically is just a time delay. And that's easiest to draw in the classical soliton case. So these are two of these solitons, little humps of energy in the nonlinear Schrödinger equation. Time is running to the right. The dotted lines are their trajectories before they hit each other. The magic of soliton solutions is that they kind of retain their identity. They come out with the same asymptotic velocity they had coming in, but they've delayed each other by a tiny bit. So the surprising conjecture, if you like, which turns out to be true, is quantum mechanics is hard in general, but maybe at long enough distances and times, you could get away with the following. The key to the Bethe-Ansatz is the phase shifts that particles make when they go through each other. That's the only remaining information. This is why higher dimensions are hard, because they're scattering angles and so on. There are no scattering angles in 1D, they're just phase shifts. A phase shift is like a time delay, according to Wigner. So maybe if I know the betha ansatz well enough, I could actually compute this velocity integral. So this is some integral differential equation, but I'll show you solutions of it. There are some analytic and some computational. Anyway, the point is that by knowing enough about betha ansatz phase shifts, things that people already knew basically, you can compute this velocity functional, and then you're done. Then you just have particles moving and slowing each other down, but never truly relaxing. And the claim is that's all there is in the dynamics of integrable models. And here is maybe a more abstract picture of what's going on and why this one kinetic theory equation is equivalent to Euler equations of an infinite number of conserved quantities. So eventually the proof is going to be in the pudding, and I'll show you that this does actually make predictions that are checkable. But here's the fact that I find remarkable about why it works. So let's go back to Lieb-Liniger, where I can actually write down the conserved quantities, and they're pretty simple. So normal Gibbs ensemble is something about particle density, particle momentum, and total energy. So it's the first three moments of this one particle distribution function. These are the conservation laws. I used this phrase generalized Gibbs ensemble earlier. That means that the equivalent of the Gibbs ensemble in an integrable system has to have many more Lagrange multipliers because there are many more conserved quantities. For Lieb-Liniger, you can think of them just as there's some UV cutoff issue, but morally you can think of them as the nth moment of this one particle distribution function. So in other words, working with the Euler equations would be working with all the moments of the one particle distribution function. If you're a physicist, then all the moments of a positive function that falls off at infinity is basically the same as working with the function itself, so this should be equivalent to an evolution equation for rho. In other words, in classical hydrodynamics, kinetic theory is just a different beast than Euler equations. Euler equations are a partial story. They're only the first three. Kinetic theory is everything. But in integral models, they're really the same thing. To say that a system is locally generalized Gibbs ensemble is essentially the same thing as saying it's described by its local one-particle distribution function. And the surprise, really the acid test that this works, is that in XXZ, as I said, the conserved charges are very complicated, and you can't even write down the new Prosen charges explicitly. You have to sort of generate them on a computer. They have an envelope, and strictly you can't write them down. But we know they exist. So you can never even write down the left-hand column, but it's very easy to write down and work with the one-particle distribution function. So is it really true that the kinetic theory that I just told you, basically this Bethe-Boltzmann equation, is the right hydrodynamics for this problem? Well, so before I show you, this is kind of the summary of what I've told you so far. Normal fluid, you've got some initial state. After a few collision times, that's local equilibrium, and then you evolve on the set of local equilibria by hydrodynamics. Integral model, you have some initial state. This is the so-called quench problem, which people know a bit about. You get local generalized Gibbs ensemble, and then that evolves according to this Boltzmann equation. So 2 Reservoir Problem was solved in those 2016 papers. We were interested in developing solutions, and there's a reason why solutions exist and so on for general initial conditions, where general means local generalized Gibbs ensemble. So I'm assuming that there's some rapid quench, but this is still a lot of states. So here are examples. So what I'm going to do is take the XXZ model in zero magnetic field. Horizontal axis is my spatial dimension. Vertical axis is energy density, because that's something that we'd studied a bit before. And what I do is I make some initial energy density at 0 by locally equilibrating the system to different temperatures. So I've made the same initial state, and then I'm going to evolve it in time by 2 approaches. One is just microscopically evolving the Hamiltonian with density matrix renormalization group, so no analytic thinking. And the other is the solution of these hydrodynamic equations, or this one Bethe-Boltzmann equation. And the point is, so one is the yellow line, that's the exact solution if you like, and the other is the hydrodynamical equations, and they're pretty good. They lie, I'm a government employee, so it's good enough for government work, as we say. They lie right on top of each other as far as we can tell. And the surprise is that, first of all, this is saying it's not just the 2 reservoir quench where we previously knew some things were special. This hydrodynamical approach works for other initial conditions. And second, that even though we're not really in the thermodynamic limit, I mean, this is 40 sites from -20 to 20, so we're not truly in the continuum, but it still works pretty well. So this would just be the two reservoir quench. What the difference between the left figure and the middle figure, and I think I zoomed in on the middle figure here, this is at lower temperature, which means things are less smeared out. So you get 2 lumps instead of 1 lump. If you want, you get 2 expansions at close to the Fermi velocity. So you can see it's not quite perfect. The yellow curve is a little bit above the blue curve. I don't know, we didn't systematically try to compute errors. Since then, people have tried to estimate what are the error terms in this approach, but they're not big. So I think I had better wrap up there. But to try to summarize the story, before we talk about breaking integrability and under what circumstances this is still useful, normal hydrodynamics is 3 equations. This is saying that, in a sense, integral models, it should be an infinite number of equations, but we're lazy. We can't solve an infinite number of equations, so let's solve 1 equation. That 1 equation is just a Boltzmann equation. The only tricky thing in the Boltzmann equation is that the velocity of one particle depends on what the other particles are doing. And I'll tell you, I think Perkis maybe had the original example of a model where that works, and we'll use that in the second lecture, but most of the second lecture will be about higher dimensions. But at least there's some class of time evolution problems of one-dimensional Hamiltonians where, with no more work than the standard Bethe ansatz, you get effectively, if you know thermodynamics, you get hydrodynamics almost for free. And as I said, this probably should have been worked out in the 1980s, but it all happened relatively recently, last 5 or 6 years. So I think I better stop there. Thank you.
In the Boltzmann equation, it just was on bracket of the distribution function with the Hamiltonian, right? So here, if velocity is space dependent, that means that the derivative of the Hamiltonian with the momentum is space dependent. So there should be a force term, right? So why is there no force term?
Well, what I know is there is a kind of Hamiltonian structure here, but it's considerably more complicated. It's like an infinite dimensional version, and technically it's semi-Hamiltonian. That's kind of the point of this paper. But basically, the same question arises basically in the classical nonlinear Schrödinger equation, and that's where Moor is known about it. So if you write this, you could ask, the main reason why we cared about this was just to be nice to know if solutions are going to exist, and there are some theorems about for Hamiltonian system solutions will exist. So here, I think it's a little more complicated because you aren't justified in thinking about any of the first few conserved quantities as special. You really have to think about all the conserved quantities on an equal footing. But there is a kind of Hamiltonian structure and a volume element that is preserved.
Yeah. Exactly. So if you don't have the term, the force term, how do you preserve Liouville theory?
There's the form of the Liouville theorem is modified now because the nature of, let's see how to put this. I guess all I can say is there is a version of Liouville's theorem that still applies in these evolution equation for integrable models. But I don't know that it's as directly connected to just X and P derivatives. But I might have to, it's a good question. I might have to think about it a bit more.
So in normal fluid, the reason why you have only the single particle distribution function is because there is a full GKY hierarchy and then you truncate it, right?
Yeah.
Why in the integral case you have only one function?
Well, I guess the way, what I would look about it is, here it works even if the system is dense. So normally the Boltzmann equation is dilute, and that's what controls the BB-GKY hierarchy, if you want. So here you could ask, well, why am I justified? And that comes down to the one thing I wanted to stress about integrability in the beginning is that the magic is that n particles coming together, the physics is the same as a whole bunch of independent two-particle collisions, even if they're all happening in a very dense way on top of each other. And that's where integrable models are special. So effectively, this says, yes, I don't need any higher interactions or higher correlation functions. In a sense, everything reduces to two-particle interactions. And that's really, but that is what's special about integral models in other ways as well, that somehow, however many particles you have coming together at a point in space, however dense it is, they all come out with the same asymptotic momentum they had coming in, which wouldn't be the case for more general interactions. Yeah. So in a sense, the order of the collisions and all that stuff is somehow important for a general interaction, but not for integral models. That's sort of the physical consequence of this Yang-Baxter relation. Yeah. But I agree, it's a surprise that it works. I mean, in fact, the paper that I credited, this Kemchatnov and L, their whole point is that it's surprising this works in the dense case, yeah, that it's not limited to the...
Because in the other case, it's really the hypothesis of chaos that gives you...
Well, that's right. Well, so here, yeah, but remember, here there's no collision term. So I guess there I'd say the hypothesis of chaos is in simplifying the collision term, which would normally be the two-particle equation, yeah. But here we don't even have the collision term, effectively, because, yeah, what the collision term is doing is randomizing momenta. You know, two momenta came in, two different momenta come out. But now we're saying in integral models, that's just not allowed. But so the only effect that is allowed is this delay. So you might say, you know, maybe you might worry. I mean, I think there are people who have given more mathematical derivations who would say that this isn't possible. But I would have worried that, OK, this delay effect is there, but maybe there are other effects. You know, how do you rule out that there's some other collision effect or something like that? But at least, you know, that was the point of doing the numerical check. Yeah. If there are any additional corrections, they seem to be extremely weak.
The XXZ model can be bosonized. Is there a useful perspective using bosonization on this?
Yes. Well, so bosonization is very useful, and there's one. OK, so in the lowest energy limit, you'll find that the system is free. So it's not just integrable, but the dynamics is very simple and things kind of propagate freely. So then you ask, let me think about corrections to bosonization, or if you want, corrections to the free boson theory. And there are a couple of interesting things that happen, and one is sort of a current research project of ours. So I guess those corrections could be either integrability preserving or integrability breaking or both. So that is to say, you could take, you know, sine Gordon, for example, is an integral model that you could view as adding some interaction to the bosonized theory. But you could also add other terms that are not integrable. So when you have both kinds of terms present, there's kind of a competition between integrability preserving and integrability breaking terms. Once you've broken integrability, the normal wisdom would be it's done. Eventually the system thermalizes, eventually linear response works, and so on. That's mostly true, but you can cook up a few initial conditions. Actually, expansion into vacuum is a case where it turns out that the integrable limit still is relevant for arbitrarily long times. Basically, as you expand, you lower the density enough that that's a case. So I guess bosonization is useful, but I guess the naive bosonized free particle limit doesn't have any of the interesting physics. It's basically just free. And then putting in higher terms, bosonization is sometimes useful, but just as a technique. I don't know that it gives you a different picture.
Can you say a little more about this, like V as a function of the particle density and how, like, what that like more explicitly looks like?
Yeah, I have a couple examples of it on one slide, I think. So it's never that simple. So I mean, this is the thing that varies from model to model, and the one that we used a lot, I should give, there's a very nice paper by these people that worked out not just sort of the principle of the V function for the XXZ chain, but in detail how to compute it. So it's related to something called the Dressed velocity, if you're a beta ansatz person. So the idea is that even if I'm not thinking about these far from equilibrium situations, people previously knew that there were cases where you solve the beta ansatz and you get some background of quasi-particles, let's say at non-zero temperature. And then I think about one quasi-particle, maybe one extra hole or something, and I ask, what is its energy-momentum relation? And it turns out that that energy-momentum relation is a bit modified because if I think about bringing the particle around a loop, it picks up a phase shift from all the other particles, which means that its allowed value of momenta are effectively shifted. Like this is what in response to Adi's question, this is what I said, what does it mean to say that my bosons have become fermions? It means that basically when I move my bosons around the others, they have picked up phase shifts like a fermion, which means that their allowed momenta become those of fermions. So more generally, the allowed momenta and, so the energy shift is there in the thermodynamics, but we also knew that the momenta were sort of modified by all the phase shifts. So I think if you don't want to think about it as a delay, which was my first picture, then you should think about it as using the Drest velocity, which is sort of dE by dP, where the energy is certainly the energy of the particle, but its effective momentum is modified by this phase shifting effect. And then the detailed form, I mean, it always takes the form of some kind of integral over all the other particles, and the kernel of that integral varies from model to model. I don't know anything very general to say about it. I mean, yeah.
It's local in space?
It's local in space, exactly. So the velocity, non-local in time, I mean, I guess later I have one very simple example. So the first kind of self-consistent velocity like this is in a classical hard rod problem, and then I can write out what it is. Okay, so I'm going to define this problem in the next lecture, but it's basically a classical problem of, instead of point particles moving on a line, think about rods of some finite length a. So a is the length of the rod. Then the velocity at a given momentum depends in this way on the density of other rods at the same point, at nearby points in space, basically. So this is a particularly simple equation where I can write down v. I couldn't write down v for xxz without a lot of notation, because xxz, for example, has, you know, in general, an infinite number of particle types. It's got one spin flip. It's got strings of n-fins. So anyway, so there it's a little complicated, but I'll come to this next time, probably just quote it, but at least in some cases it's pretty simple.
Do you have to have really the solitons, or beta particle would do? I mean, just in general.
I think you need to have a density and be able to ignore. So I think if you just have a few particles, I don't know how to write the equation and solve it. So it is kind of a continuum equation. So I mean, it works whether it's a quantum integrable model or a classical integrable model. So that is, it can just be xxz. It doesn't, you know, I don't think of xxz necessarily as having solitons. Xxz is fine. But if you took an initial state that was just like 5 particles or something, then I don't think this continuum equation would work too well. There is some recent work by people like Veer Bulchandani and Raman Vasur and Sarang Gopalakrishnan on fluctuation effects. So here I had one particle moving through a continuum of other particles. Now really that continuum is made up of particles itself, so I should get something like Brownian motion. My particle moving through should actually have some fluctuations, because sometimes it hits a particle and sometimes it doesn't, and that gives you sort of diffusive spreading of a wave packet and effects like that. So you can see particle, so if you like, the equation I wrote down is the continuum limit, and there aren't really any particle effects left. But if you ask the right question, you can see what I think of as like Brownian motion type particle effects. Yeah, so if you want linear response transport, a challenge is that the normal transports, like normal conductivity is infinite because the system is sort of ballistic. You can extract Drude weights and things like that. So as an example, I mean, this is maybe brute force. So the Drude weight was the coefficient of the delta function in something like thermal transport. So if I do the true reservoir quench, so for example, something that was done in those 2016 papers I mentioned, the problem they solved was basically the true reservoir quench and figure out, you know, if I start with, say, one chemical potential on the left and one chemical potential on the right and evolve that in time, here's what the shape of particle density looks like. And from that, you can basically read off, okay, they didn't fully do this. I mean, we may have dotted some I's, crossed some T's, but they had the right idea. You can read off from that what is the charge Drude weight, which was the thing that people had not been able to calculate until 2011 because it required this very complicated Prosen conservation law. So that was maybe the first example that, you know, just from solving the true reservoir quench, without knowing about these incredibly complicated conserved quantities, just working with this Boltzmann equation, you get the charge Drude weight from the solution. So I guess that's one example. I think other transport coefficients, energy transport is actually pretty easy in xxz because of that special property. I'm not sure about thermopower and things like that, whether people have tried.
Okay, so let's thank Joel again.